Hey folks, welcome to my channel Number Pen. Yesterday we looked at a few problems around uh, the applications of differential calculus. Now, today we're going to look at something much simpler. So we're going to look at why is dy by dx the slope of the tangent to a curve at a specific point on the curve, right? So when I mean curve, I'm referring to a continuous function, say let's call it y is equal to f of x. I want you to understand this from the basics, right? So that is why what you see on the screen out here is the picture of a simple non-vertical straight line, um, which is on the xy axis, right? Now, we all know that any line can be represented as y is equal to mx plus c. And right, and let's assume that the line passes through 2 points y2, y1, x1, x2, right? So which means that y1 equals mx1 plus c and y2 equals mx2 plus c, right? Let's try eliminating c from this equation, right? So from equation 1, let me call this as equation 1, and let me call this as equation 2, right? So I have c equals y1 minus mx1, right? From equation 1. This is this equation. What I do in equation 2, I substitute for m. I substitute for c, I'm sorry about this, plus y1 minus mx1, right? So we have an output for m here, which is nothing but y2 minus y1 divided by x2 minus x1, right? So this is nothing but the slope of the line, right? So I hope you guys are with me. So this is nothing but the tan theta, which is given by y2 minus y1 divided by x2 minus x1. See, we just saw the derivation of that starting from a straight line, right? So if we've been given two points through which the line passes, we know how to find the slope of the straight line using this equation, right? So m is nothing but y2 minus y1 divided by x2 minus x1. The reason I went through this is because this forms the fundamental of understanding why is dy by dx equal to the slope or the tangent to the curve of in of any continuous function, right? Now let's digest this formula for a minute, right? So y2 and y1 are 2 points on the continuous function corresponding to the points x1 and x2 on the same function, right? Let's do the same thing for a continuous function, which is what I've drawn below in the interest of time, right? I did not want to waste your time to sit and draw this diagram on the screen here. Let me try enlarging this for better visualization. Yeah, so we are here. We have a function y is equal to f of x, right? And we know that the slope of a straight line passing through 2 points x1 comma y1 and x2 comma y2 is given by m equal to y2 minus y1 divided by x2 minus x1. Now the picture we have right in front of us is not that of a straight line, it is that of a curve. It can be anything, right? It could be y is equal to x square, or y is equal to x square plus 2x plus 1, or it could be even a circle, say x square plus y square equal to r square. Now let's assume that we pick up 2 points, right, which are very, very close to each other. And in this diagram, I've shown it as points A and B, right? So A and B are very, very close to each other. That you have delta x out here. Let me call this out. You have delta x out here. I've just circled this is infinitesimally small, which means delta x is tending to 0, which means delta y is also infinitesimally small. So this portion of the curve, which is a very, very small portion, infinitesimally small portion, as we call what we call in differential calculus, is almost a straight line, right? And let's assume that I break this curve into infinitesimally small part, and you can imagine that each small part almost becomes a straight line, which is what forms the basis of what we are going to see further down in this particular problem, right? Further down in this particular lesson. So what we assume is I have 2 points right here, and point number 2 is x2, which is very close to x1, but is represented as, you know, uh, let me call this as dx, right, which is nothing but your delta x, right? What I've called this out as delta x out here, I'm calling it out as dx out here. And corresponding to that, you have y2 equals y1 plus dy, right? So now I go back to this equation, what we derived earlier, where we say that m is equal to y2 minus y1 divided by x2 minus x1, right? And then we rewrite this as f of x1 plus dx, which is your f of y, which is your y2 minus y1, which is f of x1, right? Divided by x2 minus x1, which is your dx, right? Now, I want to draw your attention here to this earlier statement that I made, where I mentioned that we are treating this infinitesimally small portion as a straight line because it is infinitesimally small, right? So this delta x tends to 0, right? So what we have with us is slope is equal to f of x1 plus dx minus f of x1 divided by dx, right? Now what is f of x1 plus dx is your y, f of y is your y2, right? And what is f of x1 is your y1. And what is y2? It is y1 plus dy, which is infinitesimally small. And f of x1 is again y1, and y1 and y1 gets cancelled. And that's how you have the slope of this particular equation is dy by dx, right? So you pull out any curve, you pull out any continuous function, and try to do a dy by dx of this particular function at a specific point. It gives you the slope of the tangent that is passing through the point. Remember guys, that this is not the equation of the tangent, it is the slope of the tangent at that particular point, which uh, so which passes through that particular point, right? Let me explain this using a quick diagram, right? So let me take this out, and let's assume that you have a curve here like this. Let's assume you have this point, and you have this is nothing but this line what I just drew is the tangent. Let me take a straight line and draw this so that it becomes easier. So let's assume that this point here through which this line, blue line passes is x1, right? Let me call this as x1, comma y1, right? So what we have from this particular equation is f of x is equal to f slope of the line is nothing but your dy by dx of f of x at the point x1 comma y1, right? So this is how we arrive at the slope of the line through any particular point in the curve, right, is given by the first order differential of that equation, right? So let's take an example, right? Let's say f of x equals x square, right? And what I'm going to do is I'm going to take you through this entire thing again using the above equation. So x plus dx a whole square, a whole square minus x square, and do a whole bracket of this divided by dx, right? I hope you folks are with me. What I'm doing is nothing but I'm applying this equation out here, right? So f of x1 plus dx is x1 x plus dx the whole square, right? And what do I do next? X plus dx the whole square is x square plus dx the whole square. Let me change this as well. Plus 2x dx divided by dx, right? The whole divided by. So as dx tends to 0, remember when dx is infinitesimally small, it tends to 0. The way we do this is, sorry, minus square here again, right? So your x square and x square cancels out, right? Cancels out, and then cancels out. You've got dx is infinitesimally small, so dx square becomes 0, and you are left with 0 plus the dx and dx gets cancelled, right? So you've got dx here, this dx and dx gets cancelled, and you're left with 2x. So for function y is equal to x square, the slope at any point on the curve x square is given by dy by dx of f of x, which is x square in this case, which is nothing but 2x, right? So at the point, say, x equals 4, we have slope of the tangent passing through point x equals 4 is 8, right? Which is nothing but your 2 into 4 is 8, right? So that's how we arrive at this particular, slope of the tangent to the curve equation. So in our next video, we will look at a few problems on this particular topic. So that's all for today on this video. I hope you liked my video. I'm looking forward to feedback from all you folks, and keep watching my channel. If you like my videos, please do subscribe and definitely give me your feedback as to how better we can do this channel. Thank you. Have a good day.